All right, I've got just enough time before I do the second part of this lecture to eat my nachos. Man, love this. Oh, oh, no, come back. Well, so much for nachos. I guess guess we might as well do the lecture. So we're going to do the second part of the continuity lecture. Section 2.3, I guess, part B. We're going to talk primarily about eliminating discontinuity. Let's see how good your short-term memory is. Do you remember from yesterday what continuity was? I know it's a deep thought, definitely. You can get lost in it if you're not careful. Here's the picture, right? Here's the picture. We've got two sides, a left side, a left limit, and a right limit. And we're approaching an x value c, right? That's what this says, I think, right? Is our function is approaching an x value c, right? So what needs to happen? Well, first of all, we have to be approaching the same height. And it looks like that is definitely happening here. It looks like we're coming in to the same location, the same y location, the same height. That's very good. But how do we know we're going to get continuity there? Well, this is what yesterday was all about. If you're thinking to yourself, well, the c value that x is approaching, the c value that the function is approaching, s and x value, if I plug that value into the function, it's got to generate the exact same y value, the exact same height as the limit which we are approaching. Because if I do that, it guarantees there won't be a hole there, and I will bridge the function and achieve continuity. If that's what you're thinking to yourself, then you graduated yesterday with flying colors, and you've got continuity down. If that's still a little fuzzy, keep working on it, and maybe reach out and let me know when I can help you, or come to the 3 o'clock help session. Okay. But let's go ahead and dive into the primary focus of today, which is eliminating discontinuity. And we know 4 primary types of discontinuity, right? Removable discontinuity, jump discontinuity, infinite discontinuity, and then oscillating discontinuity. Of those 4, only one of them is eliminatable. Is that a word? I don't know. Which is the only kind of discontinuity which we can actually get rid of. It's in the name, right? It's removable. Removable is the only type of discontinuity that we can remove. And we talked about that going over the homework a little bit yesterday if you watched the solutions video. So we've got 3 examples right off the bat on page 17 here. Okay, and they all give us functions that have a removable discontinuity. We don't know, I guess, the beginning of x minus 4, which has a problem at 4, right? That's where the 0 in the denominator happen, is removable. But soon we find out that because the top factors and cancels that root, that it creates a hole, and a hole is what gives us that removable discontinuity. And you can see it for yourself, of course, right here. What they're going to do in this particular example is they're just going to say, okay, if that's the issue, if that's what's causing the problem, then let's just make those go away, make them go away permanently. And our new extended function, which is actually not extended, it's actually shortened, isn't it? Is just f of x equals x plus 4. That's great, except for a couple problems. First of all, not every hole comes in a circumstance where you can just give a new function. There are different types of functions where that is not feasible. Secondly, they didn't really fix the original function. They changed the function. They changed it to something that's totally different than what it started as. And that's not really extending it. So I'm going to show you the same exact problem, and we're just going to write it. We're going to write the new function in a slightly different way. And if you learn how to do this, you're going to be golden. You're going to know exactly how to do all of the problems of this type. Okay, so here's the idea. We're going to create a piecewise function. I think, okay, personally, that shouldn't be calling it f of x anymore. F of x was the original function. So usually, like on the quizzes and stuff, it's called g of x or something different for you, okay? G of x will be the extended function of f of x. You always start with the original function, okay? Because remember, this was good everywhere except that one spot where the removable discontinuity occurred, which was at 4, right? 4 was the issue. And so what you say is that this is good unless x is 4. That's the only one bad place. So what that means is we have one little piece of work to do, and that is to determine what happens if x is 4. And this just goes back to how we learned in Unit 1 to find the y values of holes. You go to that reduced equation, which we previously have already seen is just x plus 4, and you plug in the x value where that hole is occurring and figure out the value. So 4 plus 4 is 8, and that's your extended function. So it's a piecewise function with 2 parts. I mean, I guess you could make it with more parts if there were multiple holes and you could fix them all, at the same time. But for us, it's usually just going to be one hole that we're going to fix. And so your first line is your original function, which is good as long as x is not equal to that one bad x value. And then you figure out the specific height. And if we look at the graph at 4, 8, that's exactly where that hole is happening. And so what we've done right here is we've plugged that hole. The extended function fixes that hole, and you're good. Now, there are going to be some functions, unfortunately, which will have other values which cannot be fixed, but that's not our problem. We can only fix removable discontinuities if it's an infinite or a jump discontinuity that's beyond our control. Okay. So let's take a look at the second example. This should remind you a little bit of section 2.1 when we were doing a bunch of trig relationships. And there was a really important identity that we used, and that was that the sign of k of x over k of x as x approaches 0 is equal to 1. We're going to apply that one here. I'm going to write that one up here for you since it's been, about 2 weeks, maybe a week and a half, something like that. So here it is. Limit the sign of kx over kx as x approaches 0 is equal to 1. We're going to use that one, okay? The first thing I'm going to do is kind of get it into that format, because we can see that I have a 2x here, which means I need a 2x on the bottom, but I'm missing a 2. So here's where I introduce the 2. But you can't just multiply the bottom by 2. You have to multiply by 2 over 2. Remember, 2 over 2 is just 1. So I'm not changing the value of the function. I'm just changing the way it looks. And then I can plug the 2 in the denominator where I need it with the 2. And the other 2 just floats out front. So I've just kind of tweaked my function a little bit so it's ready to go. We could have taken the limit of it right off the bat and done the tweaking as we took the limit, which is kind of how you did the problems back in section 2.1. Here is where we take that 2 and we take it outside. So 2 is in the limit, and that we're just gonna kind of move this dude out front, and that's why it ends out front. Notice once I do that, all that's left is the limit as I approach 0 of sine of 2x over 2, this right here, right? Which we know is, this isn't equal to 1. I couldn't turn this into a 1 right here, but look, now I'm taking the limit as it goes to 0, and the limit as x goes to 0 of that is 1. And so you can see it turned into a 1 right below, and 2 times 1 is 2. Now the graph verifies this to be true. The graph shows us that the limit as I come into 0 is at a height of 2, okay? But I need to fix that hole now. I need to fix that removable discontinuity. So I'm going to take, just like we did before, I take the original function, sine of 2x over x, as the first line of the piecewise function. That's good everywhere except for 0. At 0, I can't plug it in, okay? What do I want to happen at 0? So step 1, rewrite your function. Step 2, determine where it's bad. Step 3, when it is bad, right? Step 4, find the height. And that's what we had done with our evaluation of this problem over here. We found the height that it was approaching, which was a height of 2. And sure enough, that's going to plug the hole. Boom. And now we have a happy continuous function. Once again, the only type of discontinuity that can be repaired, that can be fixed, is the removable discontinuity. Your last example is this guy right here. It looks like we have to factor it up. So top is a trinomial and 2 binomials, bottom is perfect squares. This is one of those that has 2 problems in the bottom. It has the hole, which is the removable discontinuity that we will be able to fix, and it looks like it's occurring, as this says right here, right, at 3. But it also has a factor that does not cancel, and because it doesn't cancel, it's going to create a vertical asymptote, which vertical asymptotes are the cause of infinite discontinuity. Nothing we can do about that, so we just kind of ignore it. And here's that reduced function that we will use to find the location of the hole. So my challenge to you is, if you've got a little scratch paper, is to fill out that piecewise function right now. I mean, I know it's in your notes, but try not to look at your notes. Call it g of x equals, write that piecewise function. We know that the original function goes on the top line. Oops, there it goes. And everywhere except for 3, right? We would say not equal to 3. What's going to come on that second line? Take 10 seconds and finish it off. Go. Okay. So if you knew 3 was the bad spot and you plugged 3 in to find the height of the hole, hopefully you came out with a 5 over a 6. So 5, 6 is the height of the hole. And we're going to plug it up. So here goes the answer, right? Original function when x is not equal to 3, 5, 6 when x is equal to 3. We just plugged the hole. We just fixed a removable discontinuity. Now, yes, at -3, there is an infinite discontinuity. There's a vertical asymptote. That's never going away. There's nothing we can do about that. We can only fix continuities for which the limit exists. And the only continuity where the limit exists, because I'm approaching the same height, is the hole. And so we fix removable discontinuities and we let everything else go. So that's how you do these problems, and there will be a handful of these as part of tonight's assignment. It's called writing the extended function. And now you have some examples. Okay, they'll sharpen your factoring skills. You will be doing some factoring along the way. This is middle of the page 17. It's just a little reminder. You could find the same information all the way back in section 1 on page 24. When you have rational functions, how do you know what the hole is, and how do you know what a vertical asymptote is? Well, we just did a couple problems that required us to know this. So it's interesting they didn't lead off with this little fun fact, right? But if your factor cancels, it's a hole, And we just saw that. The holes are the ones that you can fix, right? There's your removable discontinuity at 2. On the other hand, if it's a factor that does not cancel, it's a vertical asymptote. And here's your non-canceling factor, right? X plus 2. And so X equals -2 will be the location of a vertical asymptote. And here's the picture that goes along with that. You see the hole at 2, 3, it looks like. I think we could fix that if we had to. The vertical asymptote back at -2. So we'll review rational function structure from all the way back from Unit 1. All right, example 2, these are kind of fun, but they can be challenging. But boy, I tell you what, they will totally test if you know the difference between continuity and the different types of discontinuity, namely removable discontinuities, jump discontinuities, and infinite discontinuities, okay? A lot of times on the test, you'll see like 2 or 3 clues for one location, followed immediately by 2 or 3 for another, and you really have to just stick with one location before you move on. Now, these examples break it down individually. So something's happening at 2, the next example has something happening somewhere else. But like I said, you could have one graph with something happening at -5, something happening at -1, and something happening at 8. And you'd have to just go through and read the clues and determine what is happening. So let me walk you through this, okay? F of 2 exists. This is big news. This tells us that there is a point. Okay, there is a point somewhere at 2. Now, it doesn't give me any specific values, y values, so I can pick anywhere I want. F of 2, I'm going to say is 4. Okay? Now, think about the idea of continuity. Think about the 3 major discontinuities we're using. Okay, we will not give you an oscillating discontinuity of this type, so it's really just the other 3, removable, infinite, and jump. What is already out of the realm at x equals 2? Think about that. F of 2 exists. If f was continuous at 2, would f of 2 exist? Yes, it would. If f had a removable discontinuity at 2, could f of 2 exist? Well, there's a hole in the graph, right? But it could be defined somewhere else, so yes. If it was a jump discontinuity, could f of 2 exist? Yes, because I could come up to this point and then move to another point, right? So continuity is still a possibility. Removable discontinuity is still a possibility. Jump discontinuity is, but infinite discontinuity no longer is. Infinite discontinuity has us moving up and down towards infinity along these vertical asymptotes, and it's impossible to have a y value at that x value. It's not part of the domain. So just by knowing that f of 2 exists, I already get rid of one of the 4 possible scenarios. There's really only 4 possible scenarios. It's either continuous or it's one of the 3 discontinuities that we work with. Now, the second clue is going to help you along the way. The limit does not exist. Well, if the limit does not exist, could it be continuous? Remember, the first condition of continuity is that the limit does exist because we have to be moving towards the same location. That's not happening. It can't be continuous. Okay. Does the limit exist for removable discontinuities? Yes, it does. Even if this point was a hole, the limit from both sides approaches that hole. That's why it's just a little hole and not a jump. And so that's out. That's out. Okay. So all that's going to be left for us is a jump discontinuity. That is all. And they don't give you any more specific information. That's it. So you just have to sketch a jump discontinuity with this parameter. So there's a number of different ways you can do this. This is one of those types of problems where there's infinitely many correct answers. A lot of students like to kind of get curvy and fancy, and they're like, okay, I'm going to come up to this point, but then, oops, kind of missed it there. But then I'm going to jump, down here and continue on. They just kind of random graphs, no big deal. Other students like to play it a little more safe, right? And so they don't want to get curvy and freaky with all the lines. So they're going to say, all right, let's say we have a hole here, and I'm going to come up to the hole with the line. It's kind of hard to keep this straight on this. That was awful. I have to start all over. So here we go. I come up to this point with a line-ish stop, right? Then I have to jump. I know it has to be a jump discontinuity, and it has to be defined somewhere at 2, so it might as well be there, right? So there's my graph, just nice and easy. In fact, you can even just do a couple vertical, horizontal lines, as long as there was a jump at 2. And you wouldn't even have to have either part of the graph that's that's been jumped defined at that point. You could have both of these be open circles like that, as long as it was defined somewhere else. Now, it does say that f of 2 exists, so you have to put that point somewhere. So as you can see, there's infinitely many different ways this can be done. But the main thing is there has to be a point at 2, and close point, and there has to be a jump at 2. Okay? All right, let's take a look at example B. This time, f of 3 also exists. So that means back at -3, somewhere along here, right? There's a point. Okay, I wouldn't fill it in until you know some more information. So let's keep reading. The limit as x approaches -3, it should be a little f in here, right? The limit of f of x as x approaches -3 exists. Okay, that's good. Because remember, we have either continuity, we have removable continuity, we have jump discontinuities. This should be a discontinuity, and we have infinite discontinuities. That's really the only 4 options that we're dealing with. And by knowing the limit exists, by knowing that we're coming to the same height, it can't be a jump and it can't be infinite. So we are already down to just 2 possibilities: continuous or removable. And we very quickly decide which one, because without hitting around on it, they tell us in this last little step here that f is discontinuous at -3. Well, if it's discontinuous at -3, it can't be continuous. So this time we have removable discontinuity, which means that when I get to -3 somewhere, they don't tell you where, so you don't have to worry about it. Sometimes they do, but here they didn't. I have a removable discontinuity, a hole. Okay? And then the only other thing you have to remember is that f of -3 does exist. So somewhere other than where the hole is, you have to define the function at -3. Once again, you can imagine there are so many different ways you could draw this as long as those 2 things happen. You have a function that has a hole at -3, and it has a point somewhere else at -3, and that's it. So we'll have some problems like that as part of this assignment too. But that's really about it. That's it today. It's just page 317. A couple more examples of continuity. I'd like you to really continue to make sure you understand the conditions of continuity. There's 2 parts, right? The limit has to exist, and the limit has to be equal to the function's value at that point to make sure there's not a hole there. I guess good luck on these problems, 19 through 39, and then a couple others. One of these is less about continuity, maybe both of them, and more about just some old-fashioned algebra stuff. Use your graphing calculators and really just think these through. So I'm not gonna hold you super accountable on 41 through 45 as far as you've got to write it up and show it. But I just want you to put a little thought into those, because it's just getting you to think about some good math. But these right here are going to be very similar to problems that you've been doing over the last, this week and last week and even the week before. So do them, work hard. Let me know if I can help you, and we'll talk to you down the road.